I'm Christy Berkman, and I'm a developer advocate here at Zillow. So today I'm pleased to introduce today's session, Text Embedding Models tutorial. And our guest speaker is Frank Liu. He's Director of Operations and Head of AI/ML here at Zillow. Welcome, Frank.
Thanks, Christy. Yeah, great to be here, and I'll get started right now. Is that cool with you guys?
They can't speak, I think.
Okay. No, I just wanted to double check with the two of you. But anyway, yeah, thank you guys. Thank everybody here. Thank everybody here in the session for coming today. Today I want to talk more broadly about text embedding models, and I wanna give everyone a heads up. This is more of a beginner to intermediate session. So if you're really, really into deep learning, or if you want to understand really, really deeply how embedding models work, what embedding model should I pick for my application? And in particular, what are some of the really, really interesting cutting edge, bleeding edge research that's being done into embedding models today? I will talk a little bit about that. In particular, I'll talk a little bit about some of the things that you want to watch out for as you pick an embedding model. But this is not, let's say, a research deep dive or a dive into a lot of archive papers, so on and so forth. This is just a very, very high level overview of text embeddings, some of the things you'll want to watch out for. And in particular, we're going to go over a tutorial of how to generate embeddings with sentence transformers later on towards the end of the presentation. But I'm just sort of going to divide this into two parts. There's going to be a tutorial at the end. I want to talk a little bit more about theory and a little bit more about, how did we get to where we are today, the history of these embedding models here in this presentation upcoming. So I'm going to talk a little bit first about sort of what are embeddings and how did we get to where we are today when it comes to them, right? And if you really think about embedding models, and if you really think about how they relate to large language models and how you can use them inside of a vector database, I think they are really, really underrated. And one of the things I like to say that I like to tell folks is that embedding models really are workhorses for AI applications. And proof for that is you don't have to look far. It's on Hugging Face, right? And if you look at Almany LML6 v2, which is a pretty popular text embedding model, it's got over 5 million downloads last month. And if you look at Llama 2, which is a very, very popular large language model, obviously there are some barriers to access, and there are other ways to use Llama 2 aside from Hugging Face as well. But Hugging Face remains one of the most popular. It has something like 700,000, less than a million downloads on a Hugging Face last month. So I think, given the just the sheer number of embedding models out there and the number of ways to generate embedding data, hopefully it's clear to you guys, hey, embedding models are really, really important for us, especially if we think about applications, not just that leverage retrieval augmentation, not just that take your data, stuff it into a vector database, but also if we think about other forms of data as well. If we think about images, you can embed those. If you think about videos, audio, you can embed those as well. You
Uh-oh.
can even embed things like graphs. You can
Is
embed
that
things like,
me?
what's that, Christy? Okay, anyway, I'll keep going. But if you really think about it, we can embed a variety of different types of data. And that's why embedding models are really, really important for us. And that's why we're going to really want to understand how they work. Now, this particular webinar is going to be focused on text embedding models, right? It's going to be focused on, in particular, a component, the retrieval component of retrieval augmented generation, and how you want to get your data into a vector database and get it out as well, right? So I'm going to continue from here. I'm going to talk a little bit about the history of embeddings first, and hopefully this will come as pretty interesting to some of you guys. I'm actually a computer vision guy. So, back in the day, you'd have these things called SIFT features, or corner detectors. I think the one in the lower right is Harris corner detection. And this is the way that you generated embeddings. Back then they were called feature descriptors in the old days, in the early 2000s and the late 2000s as well. And you would use these so-called handcrafted features or handcrafted algorithms. You'd figure out a way to represent portions of an image. Right? In the case of SIFT features or corner detectors, you'd figure out ways to represent portions of that image and use those features, stuff them into a bag, And then all those features would be a representation for that image. Obviously, pretty inefficient. You have many, many features for a single piece of data. And in the case of, let's say, TF-IDF, that is the equation. Some of you might recognize the equation. The upper right-hand corner is TF-IDF. It gives you, a lot of these vectors were very, very large and sparse as well. So that's really old days, right? And today, I think we have much more efficient ways of generating embeddings. And this is actually a screenshot from Arise Phoenix, a project that I really, really like. And it shows you that it's sort of what this shows is it's actually taking these really, really high dimensional embeddings that we generate from neural networks, and it will actually give you a visualization of what it looks like in 3 dimensions using UMAP. And I won't go into some of the intricacies of UMAP here in this presentation, but really, you can think of it as taking this high dimensional space and really compressing all of it so that we can visualize exactly what's going on in this really, really big embedding space. But nowadays, unlike before, where we had many, many feature descriptors per image, or we had, these really, really long sparse vectors that represented text. Nowadays, we can have these very, very compressed fixed length vectors to represent images, text, represent a variety of different modalities all together in the same space, right? And that is what's really, really awesome about where we are today when it comes to text embeddings, and just embedding models beyond that as well. So from there, now that hopefully we have a good understanding of a bit of the history, and the history of embeddings and the history of vector search is very, very long. So vector databases have really become popular in the past year or 2 years, but vector search has been around for a long, long time. And I want to talk about some of the ways that we can generate text embeddings today, right? And I'm going to start with recurrent neural networks, and also going old school as well. The idea behind recurrent neural networks is that you can take this sort of blue box here. This is your neural network. You give it an input hidden state, and then you give it a token. That token will typically represent, that token will typically be represented as an embedding or as a sparse one-hot input. You give it into this recurrent neural network and it gives some sort of output. There are many, many different flavors of recurrent neural networks. You can, for example, give it a single hidden state and remove all hidden states after that. You can make it sort of a encoder-decoder architecture where it doesn't necessarily output you don't read the output of the neural network at every single state until you give it, let's say, a separator token and you ask it to complete the sentence, right? You can do it, you can use it in ways that we use transformers today as well. But the idea is that it is a single model, and that model you continually feed the data back into it in order to give you the right output, or hopefully the desired output at the very end. And in particular, the embeddings that you typically get from these recurrent neural networks, while you could use, depending on the cell type that you have, you could use one of the internal embeddings. I have seen that done before. Typically, you generally want this hidden state. So that in this diagram is represented as A of T. And that hidden state is fed back into the recurrent neural network. And that is what gives you, that's sort of what maintains that sort of gives the recurrent neural network a bit of memory. And this is a really old school way to generate text embeddings. And today we have much more powerful ways of doing so, specifically with transformer encoders. And this session is not meant to be a deep dive into transformers. It's not meant to be a deep dive into, BERT versus GPT or self-attention, or all of the different variants of self-attention, different ways that you can train transformers. But really, from a high level, you can think of the transformer encoder as taking a sequence of tokens and giving you a sequence of embeddings at the output. And both of these sequences at the input and the output, they're going to be the same length. So you get one embedding per token. And that obviously has a lot of restrictions, right? So it's very, very inefficient in terms of representation. Oftentimes you have, as I mentioned earlier, you want a long piece of text or you want a whole image. You want all of that to be represented by a single embedding. This is much more efficient for you to perform search and retrieval that way. And if we fast forward a little bit beyond, the Transformer paper came out in 2017. If we fast forward a little bit beyond that, I think in 2019, there was BERT. And BERT really introduces the idea of well, I guess it didn't introduce the idea of pre-training, but it applied the idea of bidirectional pre-training to the transformer encoder architecture. And again, this is not there's lots of great articles out there about how BERT works and about some of the intricacies of BERT as well. And for those who are interested, I definitely recommend going to check out the BERT paper or reading some of the online tutorials about BERT. But really, at the end of the day, it was a way for they demonstrated how by pre-training and a transformer encoder, you can get really, really powerful results on a variety of different applications that leverage natural language understanding. And again, all these, the transformer encoder and BERT, all of these are they use mass language modeling. They don't use causal modeling. So they're not meant to do next token prediction like GPT or BARD or Llama is, but they are meant to take a sentence or take long form text and give you a representation, really help you understand, or help the computer understand what is going on in that sentence, right? And there's still a problem with BERT though, right? It still uses the transformer encoder architecture, which means that if we look at this diagram here, uh, it does look complicated. It's okay. What goes on is there's going to be an input token, and there's going to be the number of embeddings at the output is going to be the same as the number of tokens at the input. And the way that BERT typically tries to figure out whether or not two documents are related, or or any sort of variant of the transformer encoder, is that it will actually take two sentences or two pieces of long form text, add a separator in there, and then it will add a classification layer at the end across all those tokens, and you will be able to have, excuse me, across all those embeddings, and you will be able to have it'll give you a value between 0 and 1 or -1 and 1 as to whether or not these two sentences are related. That's really inefficient because it means that we have to do one inference for every pair of sentences, or every query document pair, or every symmetric or asymmetric pair. There's a lot of inefficiencies that are present in this entire process, right? If you think about transformer inference, that's not a cheap thing to do. And if I have hundreds of thousands of documents and I want to compare an input prompt, if I'm doing retrieval augmentation, or if I want to do document search, I'm comparing my input query to 100,000 documents, I have to do inference across an ML model 100,000 times. I could parallelize all of that, but it requires a lot of computational power. And it's still a very, very inefficient way to do things, even though we have a better method even though we have a better method of really understanding whether or not two sentences or two pieces of text are related to each other. So we fast forward a little bit more, and I think SBERT also came out in 2019, or was it 2020? I don't quite remember. Don't quote me on that. But it takes stock, it just takes, a regular pre-trained transformer encoder, and it adds two layers onto it. The first is pooling, and the second is it gives it a new objective function. So in the case of sentence BERT, there are actually three different objective functions that you can use. You have a classification objective function, you have cosine similarity, and you also have triplet loss. This in this particular diagram shows cosine similarity. It shows how you would how you do regression across two sentences, across two pieces of text. This is uh, it's it is not a very, very difficult thing to understand, but I think it introduced, it sort of really reshaped the way that we generate embeddings today. And I would argue that even today in 2024, most text embedding models are based on some flavor of sentence BERT. Obviously, you have a lot of exceptions out there. There's a number of really, really cutting bleeding edge papers. I've seen some papers that go back to using convolutions to help you generate sentence embeddings. But most very, very popular models today, including the one that I showed, I'm gonna go back a little bit, including the one that I showed in this diagram here, a little bit more, including the one left here, Almini LM. This one is a flavor, I would argue, of sentence BERT. And sentence BERT, what it does is it just gives you the capability to really efficiently generate embeddings. And as sentence BERT, as you train a sentence BERT model or a sentence transformers model, what happens is you have these sentence pairs. They will go through a stock BERT it will undergo pooling at the very end. This is very, very important because if you recall, in the traditional or in the original BERT architecture, in the original transformer encoder, we get one embedding for every token, which is pretty inefficient when it comes to a retrieval standpoint, right? Now we will pool across all those tokens, and then we will fine tune or we will retrain the entire neural network on some new objective that lets us perform retrieval much, much better. So instead of having, if I have two sentences with 20 tokens each, instead of having 40 or 43 tokens that I need to, store inside of my vector database, or that I need to do similarity search over, what happens here is now I just have two tokens because I've pooled the outputs of these two results, and I'm retraining the whole model using objective that I want to, using a cosine similarity objective, using a similarity objective that I can very, very efficiently run in a retrieval system, such as a vector database or any other type of vector search solution out there. And that is really the core of SentenceBird, right? So, what is the point of talking? Oh, and before I move any further, this is called a biencoder, and it gives you one embedding per text. And that is really what we want. We want a compressed single embedding representation for long form text, right? And before I talk, and if you think about it, when we at the very beginning, our goal, what we really wanted to do is to take a piece of data, in this case, it's long form text, and we wanted to transform it into a compressed representation, a single embedding, and have that embedding be representative of what it is that we're doing, what it is that we're trying to generate, and hopefully have it be good for our application, right? And if we fast forward, I sort of gave a sneak peek about some of this, but if we look at text embedding models today, you'll see that most of them are some flavor of SentenceBird. They will use, they have the typical self-supervised pre-training of masking and next sentence prediction that you have from BERT, and then they will use some sort of contrastive loss or triplet loss to train that model. And a lot of the changes that you see in these models are actually mostly related to data, but occasionally you do see changes in model architecture, training strategy. You might leverage something like sparse attention. I think Roberta does. They, instead of masking random tokens, they will mask entity tokens only, or you might use a different objective function altogether. But at the end of the day, really the way that a lot of these models operate, their foundation is in SentenceBird. They are in sentence transformers, and that's what makes sentence transformers so important for us today. When it comes to these text embedding models, I think another thing to really watch out for, and I'll talk about this a little bit in the upcoming tutorial, is that it is very, very highly data dependent. You can have what are called symmetric or asymmetric embeddings. Symmetric embeddings are saying, symmetric or asymmetric text. Asymmetric is, let's say, prompt to document matching, whereas symmetric text is just trying to understand if two sentences mean the same thing, if they have the same semantic meaning, and the ideal situations that you have different models for different domains of text as well. And I think Voyage AI does this or plans to do this. You should have an embedding model for, let's say, the finance industry. If you've ever read analyst reports, you know that these reports have different language, right? They don't quite read like something that you would find in the New York Times or something on Wall Street Journal or some of these news outlets. And likewise, archive papers also read differently than financial reports and other documents. And as it takes time for us to adjust to these types of writing styles, you also need models that adjust to these writing styles or forms of writing as well. And last but not least, text embedding models, even though some of them might have 32K token length or 1K token length, I think what you are doing is you're taking some really, really long text and trying to condense or compress it into a single fixed length embedding. Typically, it's 384 or 768, or as we'll see in the upcoming tutorial, I think it's 1024 is actually the length of the embedding, the dimensionality of the embedding. That's roughly equal to one paragraph, right? So the sweet spot is around 100 to 200 tokens, and that's roughly equal to one paragraph, right? I want to warn folks you really want to play around with your chunk size. There's no strategy of one size fits all. But from my experience, for most models, I would say somewhere between 100 to 200 tokens is a good sort of cutoff for when you would want to, for how much you want to chunk your data, right? So there's a lot of things to watch out for when it comes to text embeddings and which ones, at the end of the day, it's helpful to ask which ones are the best. And this, I actually just pulled the screenshot from, I pulled the screenshot yesterday. I believe that this is actually from the retrieval. If you go into the MTED leaderboard on Hugging Face, this is actually the retrieval tab. So it will show you the performance of all of these different models and it will rank them based on this average of a variety of different data sets, right? So for example, ask Ubuntu, duplicate questions, and so on and so forth. And all of these, at the end of the day, definitely treat these with a grain of salt. Some models perform better simply because they are much bigger. A lot of these models were trained on a lot of the same data. They might have some differences in architecture, but at the end of the day, most of them are based on sentence BERT or sentence transformers, as we'll see in the upcoming tutorial. And when it comes to, I talked about this a little bit before in previous sort of AI for developers meetup. And if you ask me what embedding model is the best for my application, I would say it's very, very highly dependent on your application requirements. All right, first thing is what are you interested in doing? If you are, what is your domain of data and what are you interested in doing? Are you interested in classification? Are you interested in retrieval, re-ranking? There are different models for different portions of your application, right? It's very, very important to understand. The second thing is, do I have enough data to fine tune my own model? And if I do, why don't I go ahead and take something that's pre-trained and fine tune against it, right? I can take, let's say, some of the ones on the MTED leaderboard and fine tune against them. How much latency are we okay with, right? If we are very, very latency sensitive, we'll probably want to pick a smaller model, like GT or BG small, right? And are we okay with false positives? And if not, we want something a little bit more specialized, a little bit more domain specific. As I alluded to earlier, oftentimes you have financial documents or legal documents. You want something that is tuned to certain industries or certain verticals so that you can get the best performance out of not just your vector database, but also out of your embedding model as well, right? A lot of this is very, very important to think about as you develop out your application, as you figure out what you want to use. If there's one takeaway that for this presentation, for this particular session, it is that there is no one right answer. A lot of it is very, very dependent and training your model, or if you have data scientists internally, training your model or picking a model if you don't. There are a lot of trade-offs involved in this. And it is, at the end of the day, an engineering question, right? What model should I pick? Which one is best for my application? So sort of coming up on the halfway mark, I have probably about 20 minutes left. So I do have a quick sort of notebook that I'd like to show everybody here. Probably won't take the full amount of time, so we have a little bit more time at the very end where I can answer any questions that are out there. But I will actually swap over to a different tab. I will take some questions at the very end as well. Swap over to a
Good
different tab.
question, Frank. In the meantime,
But
how do you apply SBERT variations to images?
That is a great question. SBERT is typically for text only, but there are a lot of multimodal models out there. So for example, any model that is trained on CLIP, so there are pre-trained vision transformers on the CLIP data set, and you can actually apply, there's also a section in the SBERT documentation for applying multimodal models to images. You just have to be very, very careful that you have a model that can support both images and text if you plan to use sentence transformers for images. That's the only thing that I would caution. If I have a little bit of time at the very end, I'll see if I can potentially show how you might want to do that. But yeah, just be cautious that you'll want to use a multimodal model. You're not going to want to use a pure text embedding model. Also, one other thing that I'll add is your pure text performance, if you use something like Clip, is going to be a little bit worse than if you used a non-multimodal model. So, all right. So there's going to be sort of three sections for this particular notebook. It's very, very short and sweet. There's a couple of different, there's also a couple of different, random examples I'll throw in here. I'm happy to take some examples from audiences as well if you guys want to try, generating different embeddings. And then I have one last blurb at the very end about sort of putting everything together, right? I know a lot of folks in this particular session probably use Llama Index or LangChain, and I want to talk a little bit about some of that at the very end as well. But before we do that, I will also make this I'll also make this notebook available online somewhere, or we'll send an email at the end of this with this notebook linked. But you will require two libraries for this particular tutorial: Sense Transformers and Milvus. And one of the interesting things about Milvus is that there is an embedded version. It's a lot, not a lot of folks know this. It's called Milvus Lite, and you can actually just pip install Milvus, and you can get a vector database that you can run inside of a Jupyter notebook, right? So I have both of these installed already, so this is going to be it's going to be pretty quick. And what I'm going to do here first is I'm going to create a model, a sense transformer model. It's very, very easy, very, very straightforward to use. And that's one of the things that I love about sense transformers. If I come back here, if I look at this is the MTED leaderboard, I'm actually using one of the models that's on there that's considered one of the top models right now. As we'll see later on, this model also has its own limitations, right? But what I'm going to do first is I'm going to instantiate the model. It really is that simple. And if you haven't downloaded this model already, because it is a pre-trained model, it will go and actually download the weights for the model before continuing. So in this case, because I already have the model downloaded, it says I can figure out, okay, what is the max sequence length? And in this case, I see that it's 512. And then to turn this into embedding, it's honestly really simple, right? I can just simply encode it. I can, there's some things I can do to play around with it. So for example, I can encode it and ask it to return a tensor rather than an NumPy array. We're not going to worry too much about that in this instance. And you'll see that it returns an embedding, and this embedding, if I do dot shape, this embedding is of dimensionality 1024. So OpenAI embeddings, I believe, are 768. You have other models out there that can be 1536. In this particular instance, for Ember v1, this is an embedding model that gives you 1024 dimensional vectors, which is also a pretty standard dimensionality. But one of the things that I want to do now is I want to take this embedding, right, and I want to show you guys here, I want to show you guys the power as well as the limitation of dense embeddings and why it is so important, depending on your application, to have your own set of data and to be able to fine-tune these pre-trained embeddings, or even take just stock BERT and fine-tune it over your own data. So I have 5 sentences. I have 5 sentences here, right? First is Zillow's is a vector data store that is amazing. Second is unstructured data can be semantically represented with embeddings. The third is related to singular value decomposition. The fourth is related to chess, and the fifth is, I guess, a sentence about pragmatism. Doesn't matter if the cat is black or white, so long as it catches mice. And what I'm going to do is I'm going to compare using this model. I'm going to compare all of these sentences together. So I'm going to ask sentence transformers to encode all these sentences with the model, and then I'm going to using this particular utility function that sentence transformers provides, I'm going to compute the cosine similarity between all those sentences and the original sentence as well. So let's do this, right? So let's try that right there. Cosine similarity in this case is the inverse, the opposite of cosine distance. So the higher the result is, the more related two sentences are. And we'll see that actually makes a lot of sense. It makes a lot of semantic sense. Zillow's is a vector data store that is amazing versus Zillow's is an awesome vector database. These two mean pretty much the same thing. And it makes a lot of sense that the cosine similarity in this case would be 0.93, very, very close to 1. Again, cosine similarity is a value that you typically get that determines how similar two two sentences are to each other. And then I can also see, it continually decreases unstructured data can be semantically represented with embeddings, and ZILIZ is an awesome vector database, is not that related, but they're still okay. So in this case, I get a score of 0.57 according to this particular model. And then it continues to go down and down. It continues to go down because these sentences, these pieces of longer form text aren't related to my initial embedding, right? Very, very
Maybe
simple.
5 minutes.
5 minutes left.
Yeah.
Okay, all right. So pretty simple, and I think there's a lot of information that's encoded into these embeddings already. I think we can see that. But I also want to go through two other examples I think that continue to show the strength and also the limitations of these embeddings. And the first I'm going to do is let's see if I can remember these. I like green and ham. Let's do that one. And then I enjoy consuming um, ham and eggs that are green. And if I do this, it actually says that, okay, this is very, very close to 1. Again, 1 is the maximum value. A similarity of 1 means that they are identical, and is very, very close, meaning that the model believes that these two are very, very similar. I can actually do this as well, right? So I can actually do that, and you'll see that it gives me a cosine similarity of 1. But I also want to show limitations of this. So I'm going to do this cosine similarity. Let's eat. And then so the first sentence is let's eat Chris. And the second sentence is let's eat Chris. And these two, because of the punctuation that's in here, they actually mean very, very different things. So the first one is, you could think of it as me talking to someone named Chris and saying, hey, let's go grab lunch, or let's go grab dinner, let's go grab something to eat. And the second sentence, because I've removed that comma, it means something very, very different. It means, it's probably not something that you would say on a regular basis. But if we look at the output of the model, sure, it's not that high. It's less than 0.9, which in this case is pretty good, but it's still a pretty high value, even though these two sentences are very, very semantically unrelated, right? If I say let's eat, comma, Chris versus let's eat Chris, these two things mean very, very different things. So this is, why did I go through both these examples? Is to show you the power of these embeddings, but also to help you understand that there are a lot of nuances here too. That if you want something that really fits well with your application, you're going to want to fine tune your own model, potentially with data like this, right? And you're going to want to, understand that this is something that is really, really important to do if you want to extract the maximum value out of your embeddings, right? So just something to keep in mind as you work with these dense text embeddings moving forward. And then I want a quick example on how to fine tune your model. It's pretty easy. Sense Transformers provides this input example sort of this class, and what you can do is you can just say you can give it a set of training examples. You can stream these examples from disk as well if you have a very, very large data set of these examples, and then what you can do is you can simply train it. And I'm only using 2 examples here because there's a lot of, because if I had more, first of all, I don't have a GPU on this laptop, and the second of all, if I had a lot, it would take a long, long time. But you'll see that after training, the shape is the same, but the results here are going to be a little bit different, right? So if I rerun this, you'll see that the weights have indeed updated a little bit. This is still going to be the same, but these results, the cosine similarity is now a little bit different. It shows you that these are actually working. The last thing that I want to go over, I know I only have a minute left, is inserting these into a vector database. And it's really pretty, I really want to show you guys, hey, you can use Milvus Lite to insert these very, very easily and be able to conduct really, really large scale similarity search across all of them. In this case, what I'm doing is I'm simply saying I am going to import the default server from Milvus, and I'm going to start it. All right, very, very simple. very easy way to get an instance of your Mobus vector database up and running. Once that's done, I can actually create a connection to it. I can use it as if it were a standard database. I'm going to create a collection, and then I'm going to insert all of those embeddings that I computed earlier into the vector database into this collection called default. All right, and then you'll see here I've successfully inserted all of these. It's got a particular timestamp. Once I'm done with all of it, I can stop the server and clean up the data as well, right? Or I should have reversed these two calls, but it's okay. Yeah, that was a bit of a whirlwind with this particular notebook. Happy to take any questions that you guys have now. Was happy to take any questions that you guys have now, and please paste them in the chat there, and we'll go from there.
All right. Thank you, Frank. Are you able to see the Q&A? I can read some off for you.
I can, give me 1 second. I can see it. So the first question is from Keen. I hope I didn't butcher your name there. I apologize. Question is symmetric versus asymmetric. I see it talked about for dynamic queries retrieving stored documents. How do I do it in reverse? For example, which library subject headings are most appropriate for this article? That is a great question. So there's some pretty interesting recent work that's done on using a large language model to create prompts or queries for a particular document. So because a large language model essentially encodes a lot of information, it gives you, it's sort of blurry JPEG of the web is one of the things I've heard large language models called. You can actually use it the knowledge stored in LLM to generate prompts or generate queries. And it actually is really, really good at that. So if I have a document, I could chunk up that document and I could ask my LLM to generate potential queries. I could say, you're an expert retriever, generate me potential queries or prompts that I can use to search for this document, or generate potential queries or prompts that that a human would write so that the document would be returned. Something like that, right? You want to play around with your prompts, but it is actually a great way for you to be able to generate data in a quote unquote unsupervised or without labeled data, to basically generate data using LLM, labeled data using LLM, excuse me. Second question is from Frank Greco. Are embeddings cross-speaking language? In other words, can I use embeddings from English to generate Italian completions? The answer, it depends on the model. So for some embedding models, most embedding models, unless they have seen enough Italian and English text, they're not going to be able to just understand Italian right out of the box. But I think even if you've seen English, if a model has seen both English and Italian text and understands that there's a lot of relationships between both of these languages, what it can do is it will actually, if you have English text in a particular domain, let's say legal documents, and then in your training data that you don't have that same type of data, as you create embeddings related to legal documents that are written in Italian, it will actually be reasonably performant. So again, if you don't have Italian in your training data, you shouldn't use you shouldn't expect any type of results from a pure English embedding model, simply because the tokenizers have never seen those Italian words. But even if you have different domains of data, as long as there's a way for the model to be able to map both of these languages together, you can actually get pretty reasonable results. Great question, by the way. Is there a limit on the sentence length that SBERT can encode? I think the answer is no. I'll have to double check. But just keep in mind that because transformers are quadratic, at least dense attention is quadratic relative to input length, you probably don't want to, here in this case, I'm actually going to try it live here, so let's see if it works. The max sequence length is 512. I can actually make it 1024. Whoops. 1024. So I can make it 1024, and I can redo all these embeddings basically. And you'll see that yes, you can do it, but as the token length increases, you get, first of all, diminishing returns when it comes to the quality of your embeddings, or you may even get worse embeddings. And secondly, unless you have a lot of memory, or unless you have a lot of CPU or GPU memory, you're going to run into those limits as you have more and more tokens. Again, because transformers, they're not necessarily inefficient, but they're just quadratic relative to input length. How is punctuation tokenized to be integrated with letters or words in embeddings? It depends on the tokenizer. And for most tokenizers, punctuation is actually its own separate token. So I wouldn't be able to answer that for you here, Brian, unfortunately. Again, it depends on the model, depends on the tokenizers that are used. But typically, I think, you can, for most tokenizers, you can think of something like 4 to 6 characters is one token. Another question from Keen, follow-up on asymmetric embeddings. I don't want to generate queries or prompts from the article. I want to match the article against pre-existing subject heading phrases. Would an LLM be necessary for this? Okay, I see what you're saying. And so my understanding, and again, correct me if I'm wrong, is that you have articles, and then you have one article, and then you have a set of pre-existing subject headings or phrases. Wouldn't LLM be necessary? If what you're doing is just trying to match these two together, you can use a standard embedding model, right? Embedding models, the great thing about sentence transformers is that it doesn't matter the order, or the order of the input, so to speak, because what you're doing at the end of the day is you're training these two sets of documents, or these two corpuses of documents together, and for every long form text, you actually get a single embedding out of it. So an LLM would not be necessary. You don't have to do anything specialized in that case. You can just match it regularly, and you'll be able to get the most relevant subject headings, or titles given a particular document. All right, I think that is all for questions, unless we have more, Christy.
I
There's a-
see some question, like a question is, are there, what kind of applications are there for embeddings besides semantic search, besides semantic similarity?
Yeah, that is a great question. So if you actually go to the MTEB leaderboard, you'll see that there's quite a few, there's a variety of different models for different applications. There's, clustering, summarization, re-ranking, retrieval Q&A, so on and so forth. There's a lot of different things that you can use embeddings for beyond matching prompts to documents, right? And there, what you want to do, what your application calls for, you want to understand that really well and pick an embedding model from that particular leaderboard, given that.
And then there was a question about multilingual embeddings. Like if you speak non-English, will these embeddings work for you?
Yeah, so multilingual embeddings, they're trained across first of all, the tokenizer can understand a variety of different types of characters, and these multilingual embeddings, we sort of touched upon them earlier, but even if you have a domain of data in one language, and you try to sort of extend that to another language, even if that domain in the second language hasn't been seen in the original training data, it will still perform reasonably well. So yeah, so multilingual embeddings, there are a lot out there. SensBERT provides quite a few as well. I didn't dive too much into that here today in this session, but there definitely are a lot of those out there, and they're very, very powerful as well.
Okay, and what if you want to embed images instead of text?
Yeah, great question. You would want to use, if you want to, depends on what you want to do. So if all you want to do is embed images, I would actually take a look at PyTorch image models, TIMM. So you can just pip install TIMM, and that'll give you a lot of pre-trained image embedding models. If you are looking to do some multimodal search, you're a little bit more limited, but any model that's trained on the clip data set, or on Laion, Laion, I'm not sure if I'm pronouncing that right, will do really, really well for your particular application.
All right, and I think we have time for one last question in the Q&A
Yeah, I
window.
see it. Yeah. How can we identify the most relevant paragraph in a document in response to a specific question or search query, particularly when we are converting the entire document into a single embedding? This is the beauty of sentence transformers, and this is the beauty of text embeddings, is you don't have to. You can, when you convert an entire document into embedding, you lose sort of internal context. So you can't pull out a very specific paragraph using that long form, using that compressed embedding. But what you can do instead is if you're interested in paragraphs, you can simply chunk your text into paragraphs, split into paragraphs, and embed each of those paragraphs. You don't have to embed the entire document, right? That's the beauty of text embeddings, that they're not fixed length relative to the number of tokens, and you can also match short form text with long form text.
All right, I think that's it, all we have time for today. So thank you, Frank. And we posted a link to the Discord. Hope to see you all online there. And thank you for joining.
Thanks, everyone, and thanks for hosting, Christy.